Good morning, everyone. Today, I'm presenting our work, PolyStore, a new system designed to reap the combined capability of heterogeneous storage devices for bandwidth-intensive applications. This is a joint work from Rutgers University, EPFL, and Samsung Memory Solution Lab. Over the past few decades, the scale of data to persist on storage devices have been growing rapidly, even on a standalone machine, for a wide range of applications. More importantly, they are requiring more and more storage bandwidth, from around 100 megabytes per second to up to tens of gigabytes per second nowadays. Along with the growing demands for storage bandwidth from applications, the storage hardware has been growing fast in the past 2 years, from NVMe SSDs to byte-addressable persistent memory with low latency and ultra-fast NVMe SSD with higher bandwidth. To fully exploit their hardware features, developers have been dedicated to developing new file systems, tailoring their hardware characteristics, as well as retrofitting existing file systems with emerging storage media by adding new features. With such versatility, using them in a collaborative way has a great potential to reduce cost while retaining the performance. Due to the performance, cost, and capacity gap between storage devices, it is natural to organize them in a hierarchical manner to high latency for slower devices. Such design philosophy has the following two classic ways. The first one is caching. New write requests are added to low latency devices, and the storage system asynchronously evicts data from low latency device to high latency devices, and we denote them as faster and slower devices respectively. For the read operations, the storage, when the miss happens in the fast storage, and the system admits data from slower storage to faster one in a prompt manner. The second one is tiering. Similar to caching, tiering also buffers data in a low latency device, which is a faster device. However, it moves data between faster and slower device in a coarse-grained manner. In both design, they use faster storage device to absorb write requests of new data. However, existing heterogeneous storage systems suffer from several pitfalls and fail to exploit both hardware and software potential. The first one is the inability to utilize combined bandwidth of heterogeneous storage because they put the device in a hierarchical layout. So when multiple threads are writing to the fast device at the same time, leaving the bandwidth of the device on the bottom not utilized at all. Taking an example of using persistent memory and NVMe SSD, we use the multi-thread benchmark to see if they can actually utilize the combined storage bandwidth. So for random write workload, neither caching and tiering approach can even approach the bandwidth limit, as well as the read workload. Because such hierarchical design circumvents the utilization of cumulative storage bandwidth. Secondly, existing systems lack flexible DRAM buffer cache mechanism for storage heterogeneity. Storage systems we know use DRAM buffer to stage write requests into DRAM and keep frequently accessed data in DRAM to high latency. However, existing systems heavily rely on the Linux page cache, which cannot efficiently handle the device heterogeneity. So firstly, the OS page cache bypasses some devices by default, like persistent memory, and cannot differentiate the asymmetrical performance of read and write operations. Moreover, it cannot provide a flexible admission and eviction control between the devices to consider their heterogeneity, because they lack a mechanism of a holistic view on top of heterogeneous storage devices. Lastly, in the system design aspect, existing systems do not consider reusing mature device-optimized file systems. For example, some approaches propose tiered file systems for certain types of devices with data placement decisions encoded in the file systems, while some approaches manage devices in a block layer, but with one file system. As we can see, both of these designs leaves mature hardware-optimized file system underutilized. The key insight in their system design is that they couple data placement decisions within the software stack. One might argue that wouldn't it be a more straightforward solution to use RAID-0 by striping data across devices to utilize the device bandwidth to consider the performance difference between them? However, as mentioned previously, this approach still encodes the data placement decision in the block layer and hides the device heterogeneity from the upper layer, like the pitfalls mentioned just now. As a result, because the block layer exposes a logical device and hides the heterogeneity, it cannot capitalize on device-optimized file systems, as well as providing device-specific DRAM buffer policies for admission and eviction control. So we argue that our ideal system for managing storage heterogeneity should first utilize the combined bandwidth of multiple storage devices. And the most important thing is it should decouple the data placement decisions and put it above the storage software stack. So in this way, it can naturally reuse the mature file system tailored for each individual storage devices with effort in the past few years, and as well as providing flexible DRAM buffer, cache eviction, and admission policies. To avoid those pitfalls, we proposed and designed PolyStore, a meta layer on top of device-optimized kernel-level file systems. PolyStore comprises two components: a user-level runtime with data placement decisions for utilizing device bandwidth, and the OS components that handles sharing across processes, resource fairness, and security. Now, let me break down the components and design philosophy of PolyStore, starting with the data indexing structure. To attain combined bandwidth of heterogeneous storage devices, the first step is to distribute data across those devices at the same time. We know that large files over gigabytes, such as data streaming files and database files, are bandwidth sensitive. As a result, PolyStore tries to distribute data blocks of a PolyStore logical file to the underlying physical files on each individual file system, which is a per file range tree data structure where each node in this data structure represents a range of blocks placed in a corresponding storage device. More importantly, this data structure also encodes the data placement and access pattern information across heterogeneous storage devices, which is the key structure for the bandwidth utilization and flexible policy for DRAM buffer cache, which I will introduce shortly. Next, let me introduce our dynamic data placement mechanism to squeeze the combined bandwidth. Maximizing combined bandwidth of heterogeneous storage devices is not trivial, because it is important to map I/O requests from application threads to the storage devices properly. The challenge lies into the following two aspects. First, as illustrated in the right figure, storage media have diverse characteristics in terms of delivering throughput for applications, as illustrated previously. Moreover, identify the optimal mapping of I/O requests from multiple threads to the storage devices in a static way cannot adapt to workload changes. This indicates that we need a dynamic data placement mechanism to maximize the storage bandwidth utilization. To overcome the above challenge, we propose an epoch-based throughput monitoring and dynamic data placement mechanism. Let me illustrate with an example. Initially, PolyStore divides the application I/O thread into two groups via writing data to persistent memory and NVMe respectively. We either split them based on some heuristic information from device spec sheet from vendors or divide them evenly. PolyStore starts moving a thread from NVMe group to persistent memory group because we want to saturate the device with higher bandwidth first. If such reassignment improves the combined bandwidth, we move another thread from the NVMe group to the persistent memory group to see if it keeps improving the bandwidth utilization. However, if it's not the case, it means the persistent memory bandwidth is oversaturated, and then we revert to the previous configuration. Eventually, PolyStore converts to a local maximal configuration that can effectively utilize the combined storage bandwidth. Then, let me introduce the DRAM buffer cache design in PolyStore, leveraging the diverse characteristics of heterogeneous devices. As mentioned previously, storage systems use DRAM buffer to storage devices to hide the latency. When using DRAM buffer on top of the heterogeneous storage devices, considering the performance asymmetry across them is crucial to use the DRAM buffer cache more efficiently to orchestrate between those devices. Because as mentioned previously, PolyStore already provides an indexing structure that encodes the data placement information of which data ranges are placed on which device. On top of this indexing data structure, PolyStore can adaptively allocate DRAM buffer cache with device-specific policies for admission and eviction control. Take the case of using persistent memory and NVMe SSD. As mentioned previously, persistent memory read is very fast, though it is slower than the DRAM, but still at the same order. Therefore, PolyStore gives direct access to read-only data on persistent memory without allocating an additional DRAM buffer. However, the write performance in persistent memory is much slower than read. As a result, when data blocks are modified by the application, PolyStore allocates DRAM buffer for persistent memory only when it is modified. In addition to the data placement information encoded, the indexing structure in PolyStore can also facilitate the data migration across devices, because such index structure can also track the data hotness and coldness as it is on the critical path for each data plane operations like read and write operation. To illustrate, let's say a range of frequently accessed data need to be evicted from DRAM buffer due to the memory pressure. Instead of traditional buffer cache, DRAM buffer cache, where data need to be evicted to its original location in slower devices. In PolyStore, because we have a holistic view on top of different storage devices, as a result, PolyStore can flush hot data on slower device to faster device if space permits. So next time when this range of blocks be accessed, it will be faster. And finally, PolyStore do garbage collection for the original data blocks on slower device. As designed as a meta layer on top of device optimized file system in the OS kernel, PolyStore brings some challenges in providing correct consistency across different file systems because they all present different and diverse atomicity and durability guarantees, as well as providing sharing, security, and fairness across processes. Please check out more technical details in our paper. We now evaluate the design of PolyStore by answering the following two questions. First, can PolyStore utilize the combined bandwidth? And second, can PolyStore provide benefit of real applications? In our experiment setup, we use persistent memory plus NVMe SSD as our heterogeneous storage configuration, and we use Nova and exe4 as our file system for persistent memory and NVMe, respectively, for PolyStore. We also compare PolyStore with state-of-the-art systems with hierarchical design philosophy, which are caching design with authors and tiering design with SPFS. We also evaluate more heterogeneous storage system configuration and more combination of using different file systems and more state-of-the-art system compared. Please refer the detail in our paper. We first studied the ability of utilizing combined device bandwidth with multiple multi-thread benchmark accessing private files, and we try to see if it can saturate the storage bandwidth. We start with the sequential append workload to study the data placement impact on bandwidth utilization. As we see in the figure, neither caching nor tiering can even approach the bandwidth limit due to their hierarchical design. However, PolyStore can achieve up to 6.1x over those approaches and effectively saturate 90% of the available combined bandwidth. For the read workload, PolyStore can also achieve up to 3.3x bandwidth more than those systems, because PolyStore provides scalable indexing mechanism and dynamic data placement mechanism to spread data across both devices simultaneously. Now let me take a further step to break down and analyze with sequential append workload on 32 benchmark threads with only static coarse grain data placement without our epoch-based dynamic approach. Initially, benchmark threads are divided into two groups, writing data to persistent memory and the NVMe, respectively. However, when the thread groups using persistent memory finishes, and the persistent memory bandwidth becomes idle, due to the lack of dynamic data placement mechanism, PolyStore cannot dynamically remap I/O requests to use PM, leaving its bandwidth unutilized. As we can see here, though the static approach can, to some extent, achieve the combined bandwidth, however, it cannot adapt to workload changes. Now let's see when enabling dynamic data placement mechanism in PolyStore. In the initial phase, there's no much difference. Later, when the persistent memory bandwidth becomes idle, as the thread groups using persistent memory have finished, PolyStore starts moving threads from the NVMe group to persistent memory, aiming to optimize the combined bandwidth utilization. As a result, with such dynamic data placement mechanism, PolyStore can distribute data across from logical file to physical files in a dynamic fashion, thereby saturate more storage bandwidth. We finally studied whether PolyStore can benefit the real-world applications, and we use RocksDB with YCSB workload. For evaluating end-to-end performance delivered to application, we enable DRAM buffer cache for all of the systems. As justified previously, the OS page cache cannot handle the device characteristic and their heterogeneity. Take an example of YCSB F workload with 50% of read modify write workload. Let's see whether PolyStore can benefit. First, if we only use OS page cache for PolyStore, it only shows marginal benefit because RocksDB is not doing I/O requests all the time, and OS page cache cannot efficiently handle the device heterogeneity for data admission and evasion control for DRAM buffer. However, if we enable such flexible control with PolyStore DRAM buffer cache mechanism, it can effectively elevate the poor write performance for the persistent memory and adaptively migrate data from NVMe to persistent memory, as described previously. As a result, PolyStore can achieve up to 1.7x compared with state-of-the-art hierarchical design systems. To conclude, as the storage bandwidth keeps increasing, the hierarchical design philosophy no longer suits bandwidth-intensive applications. Existing heterogeneous storage systems suffer from design pitfalls of hierarchical philosophy, as well as their inherent inability to explore device-optimized file system and heterogeneity-aware DRAM buffer policies. To this end, we propose PolyStore, a meta layer on top of mature device specialized file systems with a dynamic data placement to scale data horizontally across multiple devices, as well as a DRAM buffer mechanism handling the device heterogeneity. We open source our artifacts. Please feel free to try. Thanks for listening. I'm happy to take any questions.